Okay, we're going to start a new unit today, and this is going to focus most about collecting information on consumer behavior. So we're taking a turn from what we did previously about investments, stocks and bonds, and constructing a portfolio to address a more traditional marketing topic. So we're going to look here mostly about the technical details about how to collect data, but also how to use data to construct narratives that can be useful to making business decisions and informing us about how consumer behavior can be translated into a marketing strategy. So we're going to organize this under 4 general questions. The first one is, how can we construct narratives from quantitative data? And we've seen a lot with this recently, particularly with the discussion of the coronavirus about flattening the curve. Now, flattening the curve is talking about the effects of 2 different policy initiatives. One where social distancing is taken, and the other one where it's not. And what we're saying is we're producing quantitative data about how many cases are likely to happen and when they're likely to happen under these 2 different scenarios. So when we actually put up things like charts and graphs and quantitative data, how can we translate that into stories that we can tell in 1 or 2 minutes that can be used effectively for marketing? The second thing we're going to look at is what are the trade-offs in the cost and accuracy in collecting data. Now, we can have the most perfectly accurate and precise data, but it would probably cost ridiculous amounts of money to actually collect that data. So for example, instead of, let's say, if you want to track the effectiveness of social distancing, we could actually go out into the field and study in a variety of different locations and see how packed in or how distant people are keeping. But one way that one firm is actually keeping track of this is wait times at amusement parks and places like beaches and things of that sort. And what they were seeing around the world was that wait times were actually increasing in the United States, indicating that social distancing was not being taken early on, while if you were looking at places in Asia, including places where coronavirus had not spread yet, you were seeing wait times decrease. And that was a good way to kind of track the level of social distancing in different places in the world. The last thing is, how do we evaluate these inferences? Now, most things that people say, whether they're true or false or accurate or not, are based upon some type of factual information and usually some type of quantitative information. And you often see pundits as well as politicians cite statistics, but usually these statistics are out of context, and so we need to be able to evaluate different inferences that are being drawn and not just saying let the data speak for themselves. And I'll give you a 5-point kind of criteria to evaluate different quantitative claims. And lastly, we're going to look at why sometimes survey questions are more reliable than others. So when you want to design a survey, it's not just let's put the questions out there. You have to write the question in such a way that's going to collect useful information for you to use. Because it's not about getting a particular result, it's getting information that's going to undergird your action and help design your marketing strategy. So we're going to start looking at just one very simple idea of looking at how more data improves our understanding of how the world is working. So let's say we want to understand a very simple relationship between how many hours a student study and their performance on a test. So let's say I collect data on one student. I know what his grade is because the test was graded, and I can ask him a simple question like, how long did you study? So how many hours or how many minutes you study? And let's say this is a student, Adam, and they studied a moderate amount and they got a moderate grade. So they got a grade of a C and they studied somewhere in the middle of time. Now, can I actually infer anything from this data? Or is this just a story or an anecdote that maybe it can support a lot of different interpretations? So one is that if he had studied more, his grade would have been higher. So because he studied this amount, okay, what you can say is that, well, he got the grade that he could expect given the amount of effort he put in. And if he had put in a higher effort, we could move up this data point along, let's say, the arrow. Okay, so if he had studied more, maybe a higher grade, a B or a C. And if he had studied less, maybe a lower grade, a D or an F. So that's one way to interpret that. However, if this is all the data we have, it's also just equally valid to say that if he had studied more, his grade would have gone down. And some people actually might agree with this interpretation. If you study a lot, you might have too much information that might lead to more confusion. You might not have slept enough. You not be because you studied. You might have done a lot of effort information, but not enough sleep. So you're not a very. You might have psyched yourself out, or got too anxious, or didn't get enough sleep, so you're not focused on the time of the exam, and that would have decreased, let's say, your overall performance. And if you had studied less, perhaps you would have done better. However, it also could have been that studying doesn't have any impact on how your performance is, which means they're unrelated. Which means if he had studied less, his grade would have been a C. If he had studied as much as he did, his grade would have been a C. And if he had studied more, his grade would have been a C. And so generally, when you see a horizontal line like this, it's saying there's no relationship between 2 variables. Now, it's also possible that It might have been a more complex relationship. What we might have had is something that we might call curvilinear, that a little bit of studying helped, but a little more studying led to more confusion and decreased your performance, but a little more knowledge, let's say, corrected those problems, but too many hours studying led to confusion, fatigue, and other things that negatively impacted the grade. So all these things are possible. I've just told 4 different stories about how this one data point could be interpreted. So the solution to this is to collect more data. So let's say we collect data on a second student. Let's say her name is Brittany. Okay, Brittany studied less than Adam did, and not surprisingly got a lower grade. Now that we have this data, well, we can say, well, geez, now we know what happened. Studying is related or correlated with a better performance on the test, because both points fall along the line that we showed originally. And it would be harder for us to have, say, the negative, or let's say the downward sloping, because that wouldn't be consistent with the data we've collected. However, we could draw this type of curve and still say, well, all the data points still fall along the functional relationship that we are imputing here. So this is obviously not enough. And the real point and takeaway here is the point is not a pattern. All of us have points or data points, and you might say these are anecdotes or personal experiences. And so when we want to go beyond our personal experiences and generalize to a broader relationship, what we need to do is collect more data in a way to check ourselves or mark our beliefs to market. So let's see what happens if we collected more data on all the students. So we might get, let's say, a scatter that looks like this. And this generally seems to follow the idea that, yes, more studying would lead to better performance overall. However, we can see several, outliers. So in the upper left-hand quadrant, we see someone who didn't study very much at all, but got probably the highest grade on this test. And in the lower right-hand quadrant, we see someone who studied a whole lot and did really poorly. And so these might be outliers, which means things that are not part of the general relationship is the reason why they're overperforming or underperforming. But it might be that there's actually a better relationship out there than a straight linear relationship. Perhaps the best relationship is something like this. It seems to explain at least most of the data points pretty well, which means that overall, studying would probably improve your performance up to a certain point, and after that point, it'll probably decrease your performance, meaning that perhaps, let's say, if you don't sleep that night, you study too much, you're going to have fatigue, confusion, you're going to psych yourself out, double guess your answers, and that will lead to lower performance on the test. So we're going to look at this in terms of some, bigger picture with more data. The data before was just, made up data to illustrate the point, but I'm going to show you some actual data. So the first one I'm going to show you is a scatter plot of 2 things that I'm going to say are related to each other. So this shows you the percent of the popular vote in different states around the country for George Bush in 2004, and the level of vaccination rates for HPV, a sexually transmitted disease passed by a virus. It's something that you can easily get vaccinated for, but the vaccination rates varies by state. Now, what you see here is a pretty clear inverse relationship. The more popular votes that Bush got in your state as a percentage of the total vote in that state, the lower the vaccination rate is. And if George Bush got fewer percentage of the total votes in the state, the vaccination rate was higher. And if you see in the upper right-hand corner, you can see an R-squared of 0.41. That's pretty strong. If this was a social science journal, you could probably publish this result as a statistically significant relationship with a pretty good fit. And, for the most part, this is a pretty good linear relationship. So you don't see a lot of, let's say, data points in the upper right-hand corner. You don't see a lot of data points in the left-hand quadrant, indicating, even though there's a scatter here, it's not a perfect relationship. Generally, you have an inverse relationship, and you could claim, if correlation was causation, that voting for George Bush had some negative impact on the level of vaccination rates for human papillomavirus vaccinations. Now, you're probably saying, well, those things don't have anything to do with each other, right? One is a political thing, another one is a public health thing. These things aren't related, and therefore this is a spurious relationship. And I'm showing this mostly to say, look, if you have enough data, you're going to find relationships even if there's not a real relationship there. So let me show you another statistical relationship. Once again, on the y-axis, I'm showing you teenage human papillomavirus vaccination rates, and then the obesity rate. Now, this is almost the same relationship. The R-squared is 0.41, about as strong as it was before. It's a very good scatter if you were looking for a pattern. Everything falls more or less on the line. Very few data points in the upper right-hand quadrant or the lower left-hand quadrant. And a pretty strong relationship, meaning that for every, let's say, 1% change in the obesity rate, you have about a 3% decrease in the vaccination rate. That's a pretty strong relationship. Once again, if you were to go to a social science journal, you could probably publish this. But what does obesity have to do with vaccination rates? On one hand, perhaps these are more related, right? Obesity is, let's say, a health-related thing. Vaccination is a health-related thing. Perhaps people that are more obese are going to be less likely to get vaccinations. Maybe there's a relationship in their behavior there. We don't really know, but the point is that maybe this is more plausible than looking at a political data, but we're looking at two health-related data sets and seeing a relationship between them about as strong as we saw in the previous slide. So let me just take a step back, and I'm going to talk about a triangle to kind of suss out, go from correlation to causation here. So for example, we have an HPV vaccination rate. That's an objective data point. We know that pretty sure. We know how many vaccinations were. We know roughly what the female teenage population is in each state. It's pretty easy to calculate a vaccination rate. Okay? We also have some other things that are objective facts. We know, more or less, how many people voted for George W. Bush in 2004 in each state. And while you might dispute, let's say, the numbers or fraud, we're talking about relatively small things. Overall, we have pretty good data about how many people voted and what the percentages were each state. And obesity, once again, obesity is measured as BMI, your body mass index, how tall you are versus how much you weigh, and this data is collected by public health departments, relatively an objective fact. So the point about this is that these aren't biased. This isn't, let's say, people misanswering questions. This is finding three pretty objective, observable pieces of data sets, all that seem to have a relationship, but seem counterintuitive in the way that they're related to each other. So let's say, here we see the causal relationship. Voting for George Bush is negatively related with vaccination rates, and obesity is negatively related to vaccination rates. Okay? And what we see positively related to each other is perhaps two different things. It could be, for example, that voting for George Bush is related to obesity and related to vaccination rates, and perhaps the spurious relationship is obesity and vaccination, meaning that the reason why vaccination and obesity are related is because both of them are related to a third thing, voting for George Bush in 2004. It's also possible, and you can see this by the size of the causal arrows, the large arrows are from voting George Bush, one thing causing two other things. And so the point is that the relationship, the small arrow between obesity and vaccination rate, is kind of spurious, means that it's only related because they share something in common, not because one causes the other. Now, it's also possible that obesity perhaps causes people to vote for George Bush, and perhaps votes for a vaccination, affects the vaccination rate. And therefore, the reason why voting for George Bush and vaccination are related is spurious, because the real reason is that they're both related somehow to the level of obesity in each state. However, what's more likely is that we have perhaps another variable, something that we can observe. Let's call it conservatism. We don't know how to measure conservatism. It's not a thing in itself. It's not something you can hold. It's not something you can count, obviously. It's something, though, that we generally think is a thing. We understand there's something called liberalism and conservatism. The question is how we measure that. So it might be, for example, that there's something called conservatism that, not surprisingly, would make you vote for George Bush, and therefore might also depress your HPV vaccination rate. Maybe you are suspicious of medicine. Maybe you don't like HPV vaccinations because you think about it's solving for a sexually transmitted disease and therefore encouraging teenage pregnancy, and you might object to it on that ground. Conservatism could also be related to obesity because you might prefer a traditional cuisine or way of eating. You might be suspicious of things like alfalfa sprouts and sushi, and you might have higher levels of fat and sodium in your diets, and leading to a higher obesity rate. It's not the only thing that causes obesity, but it's probably going to say increase the probability that you might be obese. And at the same time, it might be also related to the vaccination rate for the reasons that I went before. So what you're seeing is that three things that are observable are really kind of showing the connections between something that's not observable. And you can use one of these observable things to maybe stand in for the thing that we can't actually directly measure. So I said I'm going to give you 5 criteria. So all of those things are factual, but some of them are probably more plausible than others. So I'm going to give you a kind of a 5-point, criteria, and the acronym here is MAGIC, about how to compare statistical relationships. So for example, the first one is magnitude. And this is, let's say, how big is the effect of variable A on variable B? And this is the slope, or the beta, and by the variance around that. So more or less you saw this in terms of like the little equations you saw on the scatter plots earlier. The larger the slope, whether it's positive or negative, the larger the magnitude of the slope, is basically saying there's a stronger effect between one variable and another. Not necessarily statistically significant, but that it has a big impact. So for example, if you were to find, for example, that a student, Johnny's grades increased 3 times faster at Mahopac versus Lakeland, you would probably want to know what's going on in Mahopac, because something seems to lead to grades going up much faster in one environment than another. And even though it might not be statistically significant, you would probably want to look a little further into that relationship if you were to find an effect that's large. The other thing is you have to compare it to something else. So yes, it's large, but compared to what? So for example, there might be a lot of different ways to improve your grade, but some of them are going to be more efficient. So the idea is that when you're looking at effects, you want to see which ones are larger than others, because you might not be able to do everything. So if you only can choose a few things to do, you're going to choose the ones that are most effective. The second thing is articulation, which means how specific your claims are. So for example, you might make a general claim like Prozac, an antidepressant drug, is effective, versus Prozac is more effective on teenage girls and middle-aged men. The first one is pretty general. The second one is articulated, which means it's saying it's more effective in one environment than another. So for example, Prozac is an antidepressant, and I'm not saying this is true, I'm just using this as an example of what a well-articulated specific claim could be, is that if it's more effective with teenage women than middle-aged men, then I might be prescribed this medicine more for one population than another. 3, generality, which means how broadly applicable are the findings. Is it only true in one environment, or is it true in almost all environments? My father used to say is that I have a spotted cow, therefore all cows are spotted, is an example of, let's say, something that is looking at only the things you understand and then generalizing from your anecdotal evidence. Another way of thinking about this is what's called a drunkard search, where it's a story in statistics that says someone was coming up to a drunk person looking for their keys, and they were looking for them in the light and the lamppost. And so the person said, "Did you lose your keys here?" And the drunk says, "No, I lost them down the road, but this is the only place I can see." So sometimes, very often, what happens is that we tend to put more weight on the things that we can directly observe and not look at the generality of information. So the question is that there are a lot of things that might be true in our local environment, like New York, but they might not do well in somewhere else. And so we want something that's more general, and if the effect seems to be more general, then we're going to be more confident about the relationship between that. The fourth is what I might call interestingness, which means, does it tell us something we didn't know before, or something that is counterintuitive? For example, the sun rises in the east 100% of the time. That's a very strong relationship. One person used to say, we have laws in political science. We have elections in the United States every 4 years. And that's probably not that surprising. It's probably not that important, because maybe it's tautologically true, or it's true for some obvious reason. It doesn't really reveal anything that we didn't know or that's beyond common sense. So the fact that you find statistical significance in that the sun rises in the east 100% of the time is not going to be a very interesting claim, and therefore that the fact that it turns out that way is not something that you're going to, in a sense, use statistics to determine. And lastly is the procedure and is the data internally consistent? Is the data good enough? And this is summarized by kind of a short acronym GIGO, which means garbage in, garbage out. If you use bad data, or your data is not really independent, and you see this a lot in terms of education research claims, where they claim to have, let's say, 15,000, 20,000 observations, but very often what you look at is that these observations are not really independent, and as a result, that because they're not independent, the statistical results that they derive from them are garbage, which means they have a lot of observations, but because they're not structured in a way that they have random and independent variables, observations, you really can't make any statistically sound inferences based upon that data. Okay, so the other one is that when you have more than one effect on something is that you might have two things impacting things. So what this table shows you is the effect of income inequality and wealth on your chances of dying in different cities around the country. And what they found is, two different effects. One is income inequality, which means how is income distributed in the urban area. The second one is per capita income, which is how wealthy that city is. So we can probably understand that maybe a wealthier city is going to have a lower chance of dying than a city that is less wealthy. More resources, wealthier people, better diet, all things can be correlated. And we can probably think that a city that's more equal is probably going to have a lower mortality rate than a city that is less equal, where there's more of a rich-poor gap. But which one of these is more important? And what you can do here is kind of find the slope of the kind of this, and we have it in two different dimensions by having kind of this three-dimensional box. We can see what the inequality effect is roughly that magnitude, and we can look at the wealth effect, it's roughly that magnitude. And if you look at the angle of, let's say, the slope of these two arrows, we can see that the inequality effect is actually much larger than the wealth effect. So that if you're looking to reduce your chances of dying, it's much more important to be in not so much in a wealthy city as in a city that's more equal. And while this is not the reason for why it's happening, one of the most unequal cities, one of the most unequal counties in the entire country is New York County, which is Manhattan, where the gap between the rich and the poor are quite large. And a lot of this happens because when you have in a very unequal society, you tend to have a very quick spread of a lot of contagious diseases because poor people who can't get medical care tend to spread the diseases, and it doesn't really matter whether you're rich or poor because contagious diseases are just going to spread. They don't really check your wallet when they decide to make you a victim of their contagion. And so a lot of things that are related to public health, which then and this happens for not just like contagious diseases, but things like clean drinking water, quality of the roads. I volunteer for an ambulance corps, and there's some very wealthy places in the area, but they all have to go over the same bad roads to get to the hospital. So if you had a medical emergency, the fact that maybe you have a nice road in front of your house doesn't solve the problems the ambulance has to go over. In Newburgh, New York, there's a bridge on Route 32 that only has a 10-mile speed limit because it got washed out in a storm. And so the ambulance has to basically slow down to a crawl to cross that. That probably adds about 30 to 40 seconds of response time. And that doesn't matter whether the patient in the ambulance is wealthy or not wealthy, has health insurance or doesn't have health insurance. So those are types of things where if it's more unequal, it will actually have an impact on your chances of dying, much more so than whether you have a lot of resources, i.e. wealth. Not that wealth does not matter, it just doesn't matter as much. So we're going to look at something about what's called selecting on the dependent variable. And you often see this problem when people are making inferences, which means like when you want to see what's working in education, people tend to look at, let's look at the brightest students in the class, or let's look at the highest performing schools. So you see this very often like, well, we don't like what we're doing in our school district, let's go study successful school districts. Well, the problem is there's not a lot of variance among successful school districts, and so therefore, when you sample that way, if you only look at one group, you're getting a biased sample. So I'm going to show you several different examples of different sampling on something that I showed you before. So on the left-hand side, you see the scatter plot of obesity rate and the teenage vaccination rate for HPV. And so on the left, you have all the data. There's data points there for 50 states. All the data is represented there. And that means we've done the work to collect data on 50 states, but that's a lot of work. So maybe let's say I want to see if I can find the same result by only sampling 10 states. So let's take a look at this. So on the right-hand side, I show you one sample where I just sampled the southern states. These are states with the highest levels of obesity for the most part. They're also the states with the lowest HPV vaccination rates. These are, maybe you could say, the most problematic states for this thing. So let me just look at them and see what the relationship is. So I count the 10 southern states. And what you see is, and if you look at the equations in the lower left-hand corners, of each graph, you see that they're quite different. In the southern sample, the R-squared is only 0.26, while in the complete sample of all the data, it's 0.41. So the goodness of fit is significantly different than it was. If you look at the intercept and the slope of the equations, they're also pretty far off. 2.0 versus 2.8, the intercept 95 versus 75. So this is quite a different relationship than what the totality of the data would show. So let's look at another sample. Let's say I'm just going to sample northern states, the Northeast. These are the healthiest states. In the sample, low levels of obesity for the most part, high levels of HPV vaccinations. We look at the equation though, we find it doesn't really fit. So you see the R-squared is much stronger, 0.54, versus the total data, 0.41. And then even though the slope is pretty close, 2.8 versus 2.93 x, the intercept is a little bit off. It's much better than the southern sample, but it's not quite there. And now remember, this is trying with only 10 data points to get the 10 or 15 data points, the work of what 50 data points might have provided. So let me just do an alphabetical sample. So let me go through the 50 states in alphabetical order and just select every fifth state. That'll give me 10 observations. Okay, let's take a look at this. Well, this is pretty good. If you look at the equation, 2.8, 2.8 for the slope. Intercept is 95, intercept is 94. That's pretty close. And even the R-squared is pretty close, 0.41 versus 0.51. So an alphabetical sample is random, and it's not related to, let's say, looking at a good or bad sample of the total evidence. There's no reason why the alphabetical order of the state makes it more likely or less likely to have certain attributes. So you have to find a random way to choose your sample. So we're going to go on and talk a little bit more about this. Why do we do sampling? Well, in this case, we had all 50 states, so it didn't really cost a lot of information or time or resources to collect that data. But a lot of time when you're collecting the total information, it won't be just 50 states, it might be thousands of individuals, if not millions. And you don't have the time or the resources to collect that much data. Now, what I showed you was that there are ways that if you only look at 10, let's say 20% of the total data points out there, you can actually get more or less the same result. So the point about this is the cost of getting each, let's say, information, particularly with surveys, versus how efficient they are. So the most expensive way, and we have this right now, we're conducting the census, that if you don't respond online to the census, there are people who are actually going to go door to door. That means you have to hire a worker to knock on doors, sometimes several times. Pretty much we know if people knock on your door, you're going to get a high response rate. 75 to 90% of the people are actually going to give you a response to your survey. The problem is that's going to cost you a lot of money. And therefore, probably, the census is a very expensive operation. We conduct it every 10 years. It provides really good and accurate data. But the problem with it is that, it's costly. On the other hand, we could have something like an online survey, like an email survey or a digital website survey. And what we find is the response rate is really low, that if you get a query, an email saying, please take this survey, less than half of people are actually going to respond to it. And even though if it costs the same to send 100 emails or send emails to 100 people versus 100,000 people, you're not going to get a response rate, and very often your response rate might be biased, given that some types of people are more likely to respond than others. And between you have a telephone, which has kind of a 50-50 response rate, 40 to 75%. It costs more. You have sometimes robocallers where a computer kind of calls people up randomly and records the responses electronically, or you can have a human caller. We do know that the more likely it's face-to-face and more likely that it's a human on the telephone, the more likely the data is going to be dependable and usable. And so even though it does raise the cost, it might lead to better information and also you're filling out the sample quicker. So the required contacts, let's say you want to have 500 in your sample, is the sample size divided by the response rate. And so you have to make a choice about the trade-off between these things. So several different terminologies for understanding how to sample when you do sample surveys. You have the target population, which is the total specifically defined set of people about whom you want to gather information. So for example, if you're doing a survey at Lakeland High School, you might do a survey of everyone at Lakeland High School, teachers, students, administrators, parents. Or maybe you're just looking for attitudes among students, and therefore your target population are only students. Or your target population might be only teachers. And so you want to keep it set to who am I actually trying to gather information about. For example, I might just want information about consumers who bought my product. If I just ask people in general about my product, but they haven't tried my product, my responses might not be good if I'm looking at product satisfaction. If I want to understand whether people are aware of my product or aware of my marketing campaign, I might make the target population larger. The sampling frame is what segment of the total population, the total target population that I'm going to survey. So let's say, for example, there are 1,200 students at Lakeland High School. Maybe I only want to survey 100 of them. So that's, let's say, the sample of the total. The sample are those who respond. So I might ask a lot of people to take a survey, but what often happens is that people don't respond to surveys. And so if I want 100 people, I might have to ask 150 people to get 100 responses. And this is the key thing. When we say something is random, it means that each member of the target population has an equal chance of being in the sample. So for example, some people respond more to surveys because they have more time on their hands, they like sharing their opinion. They might be motivated to give a response because they're happy or unhappy with how the school is doing, and therefore you might get a skewed sample. And as I said before, a lot of education research has this problem where they have a lot of observations, they have a lot of responses. However, because these are not truly random and they're not really independent, the quantitative analysis, the statistical analysis on the data is basically garbage because each person in the population did not have an equal chance of being in the sample. So we're going to turn to our last question, which is when we write questions, how do we write questions that are going to get us the type of data that we want? And I'm going to define these two as one is behavioral questions, which I'll talk about in the next slide, and attitudinal questions, which I'm going to talk about in this slide. An attitudinal question queries subjective, unverifiable, the mental state of the respondent. So generally it's asking for an opinion, and an opinion that someone might not have an opinion, and an opinion that someone might make up on the spot. So some examples of attitudinal questions could be, do you approve of the president? Do you like Mr. Brunelli as a teacher? Are you proud of your country? Should terrorism suspects be tortured? And what is your favorite color? And while these seem to be relatively straightforward questions, it'll be amazing that people do not actually have opinions about many of these things, that they make up the opinions on the spot. And so when you're asking the question, you're not really getting their true belief. You're getting to whatever they made up on the spot that when you ask the question, which means the question made the answer. The question is not just finding the answer, the question is actually making the answer. So here's some of the problems. The first one is that people lie about their beliefs all the time. One of these reasons is they want to please the interviewer. And so particularly with you have cross-gender respondents and questioners, you find that people are basically flirting to their answers. They want to give the answer that makes you like them the most. And so very often we have what are called blind or double-blind studies that prevent, let's say, the questioner from giving, let's say, a hint to the respondee to the question about what the right answer is. And so we have a lot of that where it's social acceptability. The second thing is suggested by what are called the Ash experiments in social psychology, is that people will give answers that they think that people want them to give. So, for example, in the Ash experiments, they had two different lines, one longer than the other, and they had one person who was the real respondent, and everyone else in the room was an actor, and they had all the actors give responses saying that the shorter line was actually longer. I might have that reversed, but basically they gave the wrong answer, and they finally came to the actual subject of the experiment after hearing that what defied their senses, that the longer line was shorter or the shorter line was longer, that they found that most people went along with what the majority thought and not what they actually were observing. So even when it's trying to find out an objective thing, i.e. two things, one line being longer than the other, and it's not close, we have a social acceptability and conformity. And the lastly is what's sometimes called the Lake Wobegon effect, which is that 80% of people think that they're above average. Lake Wobegon was a fictional place in Garrison Keillor's Country Home Companion, and the introduction to talking about the news from Lake Wobegon is that 80% were above average. And the reason a problem with that is that only 50% of the people can be above average. And so if you get a higher number, it's because people are overrating themselves. If you ask people like, did you do better on this test than the average of the class, you'll probably find 80–90% of students will say that they did better than most people in the class, or they're smarter than most people in the class. Reality says that can't be true. So another one is that people don't know their beliefs, and one thing that's very often said is that people have non-attitudes, which means people don't really know what they believe about products, public opinion, politicians, policies. So for example, something that was brought up under Ronald Reagan as an example of government waste, there was research on Polish bisexual frogs. If you look this up, you'll find that there is something to this, although this is not what it was represented to be by our past president. But you probably did not have an opinion about Polish bisexual frogs until someone asked you the question. You might think, well, that's bizarre or that's wasteful. And if I asked you a question like, do you think the government should spend money on research on Polish bisexual frogs, you probably would say, no, that seems like a waste of money. Because most people do not have informed or good opinions about this. The last thing is when you ask attitudinal questions, you get what's called priming and sequence problems. So that I might ask two questions in a row, and how you answer one question might change your mind or change your mental focus about how you're going to answer the next question. And they did this study of attitudes about civil liberties. And they basically gave the respondees a scenario saying a bunch of students were protesting something, and they walked down to the common of the university and gathered in the field, and should they be allowed to protest or burn the flag? So they basically told the story, without any information. And then they gave the same exact scenario, but they added in, well, the protesters walked down Jefferson Street and assembled at Washington Hall, and in the Madison Commons, they decided to burn the flag. And what they found is just by putting those extra words in that made people think about the founding, the people who wrote the Constitution and Declaration of Independence, they found that changed how supportive people were of civil liberties. And so what happens is you get push polling where they try to get a response so they can say, oh, look, people really like this. And what they do is they basically kind of give you some information that change your mind to get the result on the survey and then claim that the survey is a scientific survey, which it is not. So factual questions are a little bit better because they're asking about something that's objective, verifiable, and they're they have the respondent less likely to dissemble and less likely to lie. So a behavioral question, instead of saying, do you like the president, might be, did you vote for the president? Rather than saying, do you like a teacher, I might say, how many hours did you study for this class? Or did you watch the video? Instead of asking whether you are patriotic, I might say, what did you do on Veterans Day? And instead of asking you what your favorite color is, I can say, what is the color that most people wore when they walked into school on Monday? And that could tell you a lot more about what is, let's say, the most popular color. And a lot of research now in business and in marketing is behavioral business, but what they're doing is they're watching your behavior online. They can track whether your cursor hovers over certain items versus others, how long are you on one site versus another, and they can find correlations on that will allow you to kind of get information to put people into categories and find what things are likely to buy or what things are likely to favor versus, in terms of products. What are the advantages of this? One is that you can verify the data. If you're looking for a behavior versus an attitude, you can actually check the behavior. I can count the number of people wearing a certain color of t-shirts. I can get data on how many people voted for the president. There are things where I can see how many people watched this video, or how many hours or how much time you spent on that. And that's probably a better indicator of engagement than, let's say, asking you for your opinion. Very often what happens is that people say, hey, I like this, etc., etc. It tends to generate better data, which means it's discrete and continuous, which means it works better for the statistical models that analyze data versus like a lot of behavioral questions are kind of open-ended or more qualitative answers than quantitative answers. And finally, priming and sequence do not matter. So I'm going to get to the last thing, and like, how can you tell when data is actually messed up? And this is something called Benford's law, which means there are ways of checking to see if the numbers are truly random versus numbers that people made up. And this was used to analyze Enron, which was a a company that was faking its books about how much money and what their profits were. And the basic thing about this is that in any random sort of numbers, anything that's in a sense generated through a natural process, certain numbers should show up more likely than others. And what this is that ones show up more than twos, twos show up more than threes, threes more than fours, and we actually know what this data is. And so if you look at this in terms of on the left-hand side, I'm showing you a variety of different things that we know objectively. Numbers in the census, CPI stands for Consumer Price Index, which is a measure of inflation, the birth rate, the geographical area of countries. And what you find is that they basically form a nice slope. What you might see is that accountancy tends to be a little bit off, indicating that when people actually, numbers, when they keep their books, they don't conform to that law. And you can see, like, if you look at a pattern of numbers, just looking at digits, if they conform to this curve, they're probably naturally producing. If they don't, they're probably, in a sense, manipulated in some way. And what you see here with lottery numbers is that in lottery numbers, there are independent, which means every number is equally likely to happen. You see them having a 1/10% chances of showing up. So you see them on that dotted line at roughly 10 to 12%. On the right-hand side, you see kind of a comparison of, let's say, all the data on publicly available traded firms, and you can see that they more or less track precisely to Benford's law, as you would expect if they were not lying. But if you look at, let's say, Enron's data, you see that certain digits show up more likely than other, indicating that someone is actually making up the numbers and just putting numbers in. And because we have some biases to that, we sometimes favor one number over another. When we make up numbers, this tends to happen. And I think you see this if things that are subjectively graded, meaning things like essays, tend to not follow Benford's law, but things that are objectively graded, like multiple choice tests, do conform. And why this is important is that you can use this as a way of looking at numbers to see that are the numbers really accurate or are they manipulating them? And this is often one technique used in forensic accounting. So that's all for today. We're going to talk a little bit more about consumer behavior and some of the ways not only to get at the information, but some generalizations about consumer behavior in our next video lecture. Thank you for listening today, and I will see you soon.